December 9th, 2021. A vulnerability is publicly disclosed in Log4j, a Java logging library used by virtually every Java application on the planet. The exploit is trivial. One line of text in a chat message, a search bar, a username field, and you have full remote code execution on the server. CVSS score 10 out of 10, the maximum. 93% of cloud enterprise environments were vulnerable. The vulnerability had existed unnoticed since 2013, 8 years. Within hours of disclosure, nation state actors and botnets were exploiting it at scale. What Log4j is, how the JNDI lookup works, the full exploit chain, the blast radius, the patch nightmare, and the system design lessons. We'll cover it all. Let's go. First, what is Log4j and why is it in everything? Log4j is a Java logging library maintained by Apache Software Foundation. When a Java application needs to log something, an HTTP request, an error, a user action, it uses Log4j. It's the standard. Nearly every Java application in production uses it. And Java is everywhere. Apache struts, Solr, Druid, Elasticsearch, Spring Boot, VMware, Minecraft, enterprise apps, cloud services, embedded systems. If a company runs Java, and mostly do, they almost certainly have Log4j somewhere in the dependency tree. But Log4j isn't just a dump string logger. It has a feature called message lookup substitution. When Log4j sees a special syntax in a log message, $ curly brace, it doesn't just log the text, it interprets it. It resolves the value at runtime. This is the feature that makes the exploit possible. Log4j is in almost every Java application and it doesn't just log strings, it interprets them. That's the main problem. To understand the exploit, you need to know what JNDI is and how Log4j uses it. JNDI is Java Naming and Directory Interface. It's a Java API that lets application look up objects at runtime using a name or URL. Think of it like a DNS for Java objects. You give it a URL, it fetches the object even from a remote server. Log4j supports JNDI lookups inside log messages. When it sees $ curly brace JNDI colon, it performs a lookup. It supports LDAP, RMI, and DNS protocols. The critical one is LDAP. An LDAP URL tells Java, go to this particular server, fetch this object and load it into the memory. Now here is the problem. The JNDI lookup happens automatically when Log4j processes the log message. No special permission needed, no configuration. If user input reaches the logger and contains the JNDI syntax, Log4j will connect to the attacker's server and load whatever code they serve. It doesn't matter what log level you use. Even if you only log errors, if the input reaches Log4j, it's game over. JNDI lets Java load remote objects by URL. Log4j evaluates JNDI lookups in log messages automatically. User input becomes remote code execution. Let's trace the full exploit chain step by step. Step 1. The attacker sends a request to any application that uses Log4j. They put the JNDI payload in any input that gets logged. The user agent header, a search query, a username, a chat message, anything. Step 2. The application logs the request, Log4j processes the message, sees the JNDI lookup syntax and resolves it. It connects to the attacker's LDAP server. Step 3. The attacker's LDAP server responds with a reference, a URL pointing to a malicious Java class file hosted on the attacker's HTTP server. Step 4. The victim's JVM downloads the malicious class and executes it. The attacker now has remote code execution on the exact server. They can install backdoors, steal credentials, deploy ransomware, pivot to internal systems, anything. Send payload, app logs it, JNDI connects to attacker, loads malicious class, full remote code execution. 4 steps, 1 line of text, game over. The blast radius of Log4j shell was unlike anything the industry had seen. 93% of cloud enterprise environments were vulnerable. Hundreds of millions of devices, not just web servers, any Java application that logs user input. That includes Minecraft servers where kids were exploiting it by typing the JNDI string into the game chat. Within hours of public disclosure, mass scanning began. Botnets like Mirai and Kensing automated exploitation. Nation state actors from China, Iran, North Korea, and Turkey were observed exploiting Log4Shell within days. Attackers dropped ransomware, crypto miners, reverse shells, and credential stealers. But the worst part was finding it. Log4j isn't just in your application, it's in your dependencies. A company might not even know they use Log4j. It's buried 3 levels deep in the dependency tree. Elasticsearch uses it, Kafka uses it, Spring Boot uses it. If you run Java in production, you are almost certainly vulnerable. 93% of cloud environments, nation state exploitation in days, and most companies didn't even know they were running Log4j. The patching was a nightmare. 4 CVEs, 4 patches, and even one revealed another problem. Version 2.15 was the first fix. It disabled JNDI lookups in the log messages by default. But within days, researchers found a bypass. CVE 2021 45046. Certain non-default configurations were still vulnerable. Version 2.16 removed message lookups entirely and disabled JNDI by default. But then a denial of service bug was found. CVE 2021 45105. Self-referential lookups could cause infinite recursion. Version 2.17 fixed the recursion, but then a fourth vulnerability, CVE 2021 44832, was found, a remote code execution through the configuration file. Finally, version 2.17.1 patched everything, 4 CVEs in 3 weeks. But patching the library was only half the problem. You had to find every instance, every application, every microservice, every third-party vendor. Companies ran dependency scanner across thousands of repositories. Some found Log4j in places they didn't expect. Build tools, test frameworks, monitoring agents. 4 patches in 3 weeks. Each fix revealed another bug, and finding every instance of Log4j was harder than fixing it. What are the lessons? And how does this apply to system design? Lesson 1. Never trust user input, even in logs. Log4j treated log messages as executable expressions. Any data that reaches your system from outside must be sanitized before processing, and logging counts as processing. Lesson 2. Know your transitive dependencies. Your application security is only as strong as its weakest dependency, and you probably don't even know all of them. Use SBOMs, software bills of materials, and dependency scanners. Lesson 3. Powerful features need escape hatches. JNDI lookups in log messages were a feature, not a bug, but there was no way to disable them without upgrading the library. Powerful features should be opt-in, not opt-out. Lesson 4. Defense in depth. Even if Log4j was vulnerable, egress filtering, blocking outbound connections from app servers would have stopped the exploit chain. Network segmentation, WAF rules, and runtime protection all add layers. Sanitizing all input, including logs, know your dependencies, make powerful features opt-in, layer your defenses. How do you bring this up in a system design interview? 5 patterns. Pattern 1. Input validation at every boundary, not just the API layer. Log4Shell exploited the logging layer. Every system boundary where external data enters, validate, sanitize, and encode. Pattern 2. Dependency management as a security concern. When you design a system, talk about how you manage dependencies, pinned versions, automated vulnerability scanning, SBOMs, transitive dependencies are attack surface. Pattern 3. Principle of least privilege for features. Log4j's JNDI lookup was powerful but shouldn't have been enabled by default. In your designs, dangerous capabilities should require explicit opt-in. Pattern 4. Egress filtering. If an application server can't make outbound connections to arbitrary hosts, the JNDI exploit chain breaks. Network segmentation and egress rules are defense layers you should mention. Pattern 5. Rapid incident response. When Log4Shell hit, companies that had S-bombs, dependency graph, and automated patching could respond in hours. Others took weeks, designed for patchability. If you found this useful, like, subscribe, and stay secure. See you in the next one.